So, yeah, as Pascal already said, I'm going to present the paper Neural Maps, Structured Memory for Deep Reinforcement Learning. And just in case anyone is confused, I'm referring to a slightly newer version of the paper than the one that was on arXiv. So this was presented at ICLR 2018. So let me quickly motivate what the problem is that the authors try to solve. So assume we have a maze like this one, and we want to train a reinforcement learning agent to solve mazes like this one. So, and if the agent is able to observe the entire maze, so if the state is the entire layout of the maze, then it's quite conceivable that that we can train an algorithm that will, or that we can train a reinforcement learning agent that will actually find some path from the start to the goal. However, in reality, what the agent is actually going to see is more akin to this. So the agent is probably just going to have access to a part of the environment, and in this case, something like the corridor that the agent is currently in. So, and if we only have such a partially observable environment, then we basically need some memory. So the agent needs to remember landmarks in the maze to be able to actually traverse such a maze. Otherwise, it will basically just act reactively, and yeah, basically strange things will happen. It won't be likely that we will see any nice behavior. The next step is that what the agent is actually going to see is probably a 3D rendering of this 2D environment. So he's probably going to see something like this. So to summarize the overall scope of what we're trying to solve here, we have a reinforcement learning setup where we have a partially observable state and we have a sparse reward. So the agent only gets a reward when it actually reaches the goal. And here we assume that we have a discrete set of actions, and our goal is to find a policy for navigating arbitrary environments. One thing I already mentioned, if we have such a partially observable environment, then we need some kind of memory in the agent for the agent to be able to actually solve this maze. And the authors claim that just using long short-term memory units will not really work well, at least for some tasks inside these mazes, because these tend to forget quickly. On the other hand, if we use external memories, such as the differentiable neural computer, which I'm going to talk about a little bit more in a minute, you'll get problems with interference. And the authors, so this is basically the take-home message. The authors try to reduce this interference within this external memory network by incorporating a sense of locality into the memory access. So here's a quick overview of my talk. I'm first very quickly going to go through some background. Then I'm going to talk about the architecture that the authors invented. And then I'm going to take you through the empirical evaluation that the authors performed, followed by some quick summary. So let's start with a very quick overview of which kinds of external memories can be attached to neural networks. Basically, the authors distinguish between two types of memories: those without a write operator, which means that the network itself cannot write data to the memory. What's written to the memory has to be decided by the person who designs the memory system. And also, often this is implemented as a convolutional network over the past M states. So the designer actually needs to decide how large this M is and what the states are that are actually being stored in the memory. And on the other hand, we have networks or external memories with a write operator, for example, this differentiable neural computer architecture, where the neural network itself actually has access or write access to the memory. And the idea is these access operators are differentiable, so we can compute a gradient and incorporate this memory directly into our learning procedure. Now, here's a very quick overview over one single slice of this differentiable neural computer architecture. So it's much more complicated, and I'm only going to give you a simplified overview over the read and write memory procedures in order to give you a sense what the problem with interference is that the authors are trying to solve. So essentially what we have is an external memory matrix which has a width and height, and we're basically trying to implement an associative memory. So we want to associate a context with a value. And when we have some context vector that is similar to the context vector that was used to store the value, then we want to retrieve a vector that's also similar to the value that we stored. One way to implement this, and the way it's basically implemented in the differentiable neural computer, is that this recall or read operation is just a matrix vector multiplication, and the write operation, if you ignore this part here and assume that it's 1, it's basically a sum of outer products of the context vector and the value vector. And now, as you can imagine, the problem is if as you sum these outer products together, as you stack those together, it's getting harder and harder to actually recall the correct value that you stored in the memory. So this is basically, in a nutshell, where the interference comes from. Lastly, for background, basically what the authors are using to train the network is the reinforce algorithm, or this particular variant, the asynchronous advantage actor critique algorithm. Basically, this just means that we have a baseline which is set to an estimate of the value function. And yeah, so these are basically these two equations that you probably implemented for the assignments. And the policy that we're trying to find is here implemented as a deep neural network. And what exactly the architecture of that network is exactly what I'm going to talk about now. So this is my attempt at visualizing the network architecture. So it might look very confusing, but I'm going to take you through it, so no worries. Basically, the main idea that the authors have is to replace the memory matrix with a memory cube. So instead of just let me go here. Instead of just having this one matrix, we basically, for each xy position in the matrix, we store an entire column. And now the crucial idea is that we restrict write access to this memory cube to a certain location. And in the case of this agent trying to navigate a maze, this location in the memory corresponds to the position of the agent in the maze. So as you can see here, yeah, basically when writing to this memory cube, we're only writing to a certain position. And this basically prevents interference because we do not update the entire memory in each time step. All right, and this entire architecture is basically defined as a set of equations that if you plug them all together, basically gives you the diagram that I just showed you. So let's quickly go through this. The first operation is a read operation, where the idea is that we want to summarize the content of this memory cube in a single read vector. So basically, we compress the entire memory cube to a single vector of dimensionality capital C, and we're doing this by training a neural network or a convolutional neural network that's actually trying to extract important information from that memory cube. Then the next step is decoding what's called this context vector CT based on the input ST. And here the idea is that we first compute this query vector or Q vector QT, which basically is a linear combination of the current input ST, so this is the partial observed state, and this RT that we just decoded from the memory cube. And then we use this vector and compute the similarity of this vector to all the column vectors stored in this memory cube, which gives us these scalars AT. We normalize these to basically get a probability distribution and then compute the weighted average of the memory content according to these alpha t, and this gives us this context vector. The next step, if we want to update the memory, then we're computing this write vector, and we're writing to the location or the position in the memory cube that corresponds to the position of the agent in the world, which is this xt, yt. And basically, again, we concatenate all these things that we've computed or received so far, plug them into a neural network, and that gives us this write vector. And when writing to the neural network, then this is what this equation shows, basically only update the memory cube at the current location of the agent, but copy all the other entries. The last step is to actually compute the policy. So here we compute this output vector by simply concatenating these three vectors. Then again, plug this into a deep neural network, compute the softmax, and this is what will give us the policy. All right. What the authors actually extend this model a little bit in some of their experiments. So one of these extensions is that the write operation actually uses the equations from gated recurrent units to basically disable or weaken access to the memory. So the agent has the possibility to not always override the memory content. This is essentially what this does. Then in the 3D environments that I'm going to show you, there's a problem. So basically the spatial space that the agent is in is larger than the memory matrix. And now if you imagine that the agent writes to a certain location in this memory cube and then moves, but the new location also maps onto the same position in the memory cube, then the agent will basically read what it just wrote to the memory, and empirically, basically the agent was confused, in quotes. And the authors mitigate this problem by using an LSTM. So basically the agent has the chance to learn to remember that it just wrote something to the memory, and they implement this by basically adding this additional vector ht and then computing this context vector ct of this vector that's computed by this LSTM instead of just plugging the raw vectors in there. The last thing is that you might have asked yourself, well, an actual robot never has access to its global position, so this is never going to work in practice. And the authors basically solve this problem by using egocentric navigation. So the assumption is that the agent knows which direction it actually went into, and then it just writes to the center of this memory cube, and whenever it moves, it updates the memory location by translating it in the inverse direction. Okay, this brings me to the actual empirical evaluation. Basically, the first experiment that the authors did is very similar to what I showed you in the very beginning. So we basically have these randomly generated mesas. And these are varying in size, and the authors hold back 1,000 mesas for testing. And essentially so the task is the following. The agent basically starts up here, and it sees this indicator block, which is this one, which can either be blue or green. And if it's blue, then the agent only gets a reward when it visits the teal goal, and if it's green, then the agent has to visit the red goal. The observation that's actually provided to the network is basically this slice, which is an RGB image that's generated from the local environment of the agent. So I forgot to say, so this yellow block is the location of the agent, with the orientation being indicated here. And the output of the network is just one of three actions: moving forward, turning left, turning right. So this first experiment basically compares the performance of the network through various epochs, where one epoch is 250 concurrent steps in multiple environments. And essentially, as you can see, if you just use the if you just use an LSTM network as a memory, then you'll get very quick convergence, but the performance is not extremely good. If you use one of these memory networks that the authors, or that I talked about, quickly mentioned in the beginning, then you actually get very quick convergence and a passable performance. If you use the neural map algorithm or neural map network that are introduced, then it takes a while until the agent basically does something meaningful. And if you use the skated recurrent units, then this happens a lot earlier and you get better performance and it's also more stable. So here's the table from the paper that summarizes the main results. So basically they do experiments with varying sizes of the memory, and they also do an experiment where they inject the position of the agent into the state vector, basically to test whether the agent is able to extract its global location from the state without this position. Because the hypothesis is if you inject this position vector, then the performance shouldn't get much better if the agent actually uses this. And as you can see, for example, by comparing these two lines, this is actually the case. And overall, the performance of the neural map network is much better compared to the prior art that they're comparing to. However, for some experiments, or in particular for this experiment, the improvement that you get is significant, but not that tremendous. So even with an LSTM, in some experiments, you still get 91% performance, which corresponds to, in 91% of the cases, the agent actually finds the correct goal. All right. Now to the 3D environment. So here we, as I told you in the beginning, the idea is what the agent would see in the real world is basically a 3D rendering of this maze and not a top-down view. So this is what's being tested here. So again, the authors are generating a random 2D maze, which is rendered in 3D. They hold back 10 mazes for testing. And the input is an RGB image looking like this, and the output, again, are these three actions: moving forward, turning left, turning right. And now, here, in this case, we test 3 tasks. So the first task is, again, this indicator task that I already talked about, where basically a signal at the very beginning tells you which goal you have to, the agent has to look for. Then we have this repeat task, where the agent basically finds a goal, or once the agent finds a goal, it's basically reset to the beginning and has to find the goal again. And the idea is it has to do this under time pressure, so the episode is terminated after a fixed amount of time. And the idea is that if it is able to remember where it found the goal, then it should be able to do this fairly quickly. And then we have this task, which is the Minotaur task, which is called like this for whatever reason, where the agent has to search the goal and then backtrack to the start location. And just to give you an idea of what this looks like and also what's going on in the memory while the agent is performing such a task, I have these examples. So basically, the agent is starting at this indicator, and you can see that it basically writes something to the memory at this location. So what this picture actually shows is this correlation or similarity of each of these points with a query vector that's generated in the neural map network. And this picture basically shows this after going through the softmax stage. Now, basically, as the agent moves along, something interesting happens as soon as the agent sees the goal. So in this example here at the bottom, the agent can see the goal. And basically, as you probably saw, somehow the color of this memory map image flips. So basically what's going on here is it's comparing its current state to all the other states that were stored in the memory map. And since it sees the goal, it has learned that this state is maximally different from the state where from its beginning state, or from the state at the start location. And so basically, once it sees the goal, you can see that this point, which previously was white, is now black because it's maximally dissimilar to the start location. So this is basically something that the agent learned to take into account. So here's another example with egocentric motion. So as you can see, the agent always writes to the center of the map, and as it moves around, basically, yeah, you can't really see very well what's going on because the memory content is shifted around. And here are the results. So again, for this simple indicator task, the memory performs really well, but the networks that we're comparing against are also not doing bad, especially for small maze sizes. Where this architecture really begins to shine is basically in these more complex tasks. Basically, as you can see here, we still get a very high reward, even in relatively large mazes compared to this LSTM memory, which means that the agent actually remembers the goal location and is able to quickly return to it. And basically the same is happening in this third task here. So this already brings me to the end of my talk. To summarize, the neural map architecture is an extension to the differentiable neural computer architecture that takes locality into account, and in this case, locality is the position of the agent, or refers to the position of the agent in its environment. The experiments showed superior performance to prior art in navigation tasks in these partially observable 2D or 3D environments. However, at least for some experiments, especially the simpler experiments, there's a surprisingly small gain compared to simpler memory networks. And this is basically partially my idea. So future work should demonstrate that this basically scales to higher dimensional or more abstract tasks and larger environments. And the authors should, in my opinion, also test this with stochastic, partially observable states. So basically, if we remember when we talked about POM-DPs in class, we basically had a slightly different notion of what partial observability means. Basically, we had this probabilistic graph. And then it might also be interesting to extend the concept of locality to other modalities than position. And yeah, that's it. Thank you for your attention. And yeah, if there are any questions, we can discuss.